Hello, hi. So thanks for the introduction. Thanks to the organizer to having put up such an amazing workshop and to having me here. And I have to apologize with some of you that already saw these results last year at CQT when I gave a similar talk to this, but however, I have some new stuff, so it's fine. So let's start right from the beginning to understand why the impact that resets has on quantum computer in general. So we started by asking this question and experimenting with a very simple experiment. We took a processor from IBM because that's what we had readily available at our disposal, which we up to 7 qubits, which is not much. And we just tried to reset the qubit and then measure the fidelity of the obtained state. Okay. If you do this simple experiment, you discover that basically you have these points, the number of qubits on the x-axis, the fidelity on the y, and you have the fidelity for 1 qubit register reset, 2 qubit register reset, etc., and you see how this fidelity goes down from the experimental point. Turns out that you can treat this decrease in the fidelity by using the assumption of the qubits having a finite temperature, a reset, which kind of goes on the same lines that the colleague was discussing earlier. And you can, so you can approximate your fidelity scaling as a function of the number of qubits as something that depends on a temperature, which will be finite, and you can fit, okay, from the data, and fitting this parameter beta on the data, which is the dashed line that you can see here, allows you to extrapolate at higher numbers of qubits. So you can see that even for single qubits that have a very, a decent, good single qubit fidelity reset, okay, when you start scaling at multi-qubit registers, up to, I don't know, 100 qubits, your fidelity dramatically decreases. And so you're basically screwed up from the beginning, because even just from the reset operation, your fidelity is already below 0.5, doesn't bother starting with the unitaries, right? So if you don't believe this fit, because to be honest, I could have fitted any function in 7 data points, don't believe this, believe this other graph where these points are points taken by the Google Supremacy paper. They provided all the data openly. And so if you do the same fit with the temperature, you can see again that this decreases, if you fit that beta, the fit is practically perfect. And again, if you have a large number of qubits, this thing goes down really, really fast. Okay, so given that, the question that we want to answer is, can we exploit cooperative effect, so collective effects, when we go to reset multi-qubit registers? So can we do better than resetting qubits one by one and use the fact that we have to reset 100, 1,000 qubits to actually kind of mitigate some of these terrible scaling effects that we observed? So that's what we did, and we tried to construct a protocol that we mutuated by this paper of João Parrondo of 2001, in which he implemented a Szilard engine, and we basically took his protocol and reversed the arrow, so that now is an Erasure protocol. So basically what you do, you take a Ising model, a Ising Hamiltonian of this form on a 2D square lattice. And you know that this has a phase transition. You can solve it analytically. And our protocol goes as follows. You start in the ferromagnetic phase with all the qubits, and all the qubits at that point are to be reset. So they are initialized at random, but you start with a ferromagnetic connection, in the parameters that would be in the ferromagnetic phase. Then you slowly turn down your coupling to cross over in the paramagnetic region and effectively decorrelate all these qubits. Then you turn on the magnetic field, the local magnetic field on each qubit to polarize them onto the direction that you want to reset on. And while you turn on the magnetic field, you slowly cross over again into the ferromagnetic region when kind of the qubits become locked in the ferromagnetic state that you have put them into, and then you can safely turn down the local magnetic field, and the qubits hopefully will remain aligned into that direction that you choose. Okay, so that's the idea. The next step is that can we implement it on a real system and test if this idea works? So it turns out that we kind of can with some limitations. So we needed a controllable spin Hamiltonian, and we used one of the D wave. So this is the Hamiltonian of the D wave, and I'm going to explain you briefly what all these terms in the Hamiltonian can or can't do. So basically you have these two terms, A and B, that are two terms that can be controlled by this parameter S, which is the schedule parameter that goes from 0 to 1, and it has a time dependence that you can specify. Okay, it's at your disposal. But A and B are not completely independent, but they are kind of interdependent. So if you go, like if in your protocol you go linearly from S equal 1 to S equal 0.5 and back, A and B will follow these curves and not be completely independent from one another. Okay, so you have freedom in the choice of S, but A and B are dependent somehow. Then you have this parameter G in front of the local field that can be independently controlled. And then you have the couplings that are the ones that we will need to form the 2D easing model in the ferromagnetic configuration that have no time dependency. So the time dependency is given by B here outside. And you can set them all to the same value. That's what we did. Okay, you can also set them to different values, but we wanted to have the Hamiltonian with the exact like phase transition to have some theoretical certainties. Okay, so basically you can rewrite this effectively as a Hamiltonian in this form, where you have these three time-dependent fields that you can control not completely independently, as I explained to you, but you have a good amount of freedom at your disposal. So what we did was to experiment with two kinds of protocols, one in which we didn't turn on the transverse field, okay, so the sigma x, and one in which we turn on the transverse field, okay? Now for the rest of the talk, I'm going to call them the quantum and classical protocol. Okay, quantum where we turn on the non-commuting term of the Hamiltonian. You can see here the plot of these protocols in the phase space, and just to like this orange curve is the analogous of the schematic depiction that I showed here. Okay, you cross over the phase transition, that is this black dot, you turn on the local field, and then you come back and close the circle, okay? So what are the results? Well, we started with playing with a 16 by 16 Ising model, so 256 qubits. In D-Wave, we have a lot of qubits at disposal, and initialized randomly at plus minus 1, and we did this protocol sampling the magnetization at intervals of 1 microsecond, and note that the protocol is pretty slow, okay, it's 40 microseconds, so it's kind of adiabatic, I would say. And we repeated the protocol 2,000 times in order to sample the trajectories, and what you have here is the trajectory of the average magnetization in time, okay, over the 2,000 trajectory. So this is the density, the probability density of this 2,000 trajectory. And you can see that for the classical protocol, we managed to reset a fair portion of the 256 qubits. So we put them in the up state successfully, but quite not close to 100%, and still like having some like noticeable variance in the distribution. In the quantum case, however, you notice that there is this like sharp kind of alignment of all the qubits in the up direction, and we are able to substantially have close to 100% qubits in the reset, like in the correct reset state we're hoping for. And this down here is the paper where we first did this thing with Michele Campisi. So another cool thing about this protocol that we implemented is that we could also estimate the energy cost of running this thing. So we write down the energy cost as the integral of the magnetization in fields, and we can directly measure the Z components, so the work done by the local fields and by the couplers, but we cannot measure in the X basis, okay, on D-wave. This is a limitation that we had, but we can upper bound the absolute value of the X of the contributor to the work done by the transverse field, and we can put it like as part of our uncertainty of the estimate, okay? So what are the results when we go to estimate the energy cost? Well, on a per spin basis, so the work normalized by the number of spins, we get that we get a value of work which is comparable with the Landauer bound at the temperature that we estimated, okay? There are various techniques to estimate the temperature inside a superconducting quantum computer, so we picked a couple, we had two consistent estimates, and if you compute the value of the Landauer bound for that temperature, this is consistent to the per spin energy that we use to reset the system. Of course, this is not the global energy that has been used by the computer, because then you have the attenuators, the signal generation, etc., but on a microscopic level, we are at the Landauer bound, so we are doing as good as we could be. That's probably also because the protocol is very slow, as I tell you, okay? So, again, erasure at Landauer cost, so that's cool. We can reset like a large portion of qubits. We see that doing this with a transverse field really helps, okay? So really helps aligning your qubits into the direction that you want. But we were left like with a fair bit of question regarding like how this is, our protocol was impacted by the parameters. So how really is important the cooperative effect versus just introducing the magnetic field, how those numbers compare with just doing the protocol without any couplers at all, and most importantly, what does this protocol perform in terms of fidelity? Because now I talk about average magnetization, but I didn't talk about fidelity, which are two different beasts. So let's first talk about the parameters that impact the success of the protocol, and these are still results that should come out soon if I can put myself to write a proper draft for the work. So for the classical and quantum protocol, we explored the different local strengths of the local magnetic fields. So on the x-axis is higher strength of the local magnetic field using during the reset protocol. And what you see are different curves for different lattice sizes. So the blue curve is with no couplings, so the individual reset protocol. So the vanilla with no couplings, no interaction. And the green one is of a 5x5 Ising model, and the red one is a 10x10 Ising model, okay? So as you can see in the classical case, basically the cooperative effect is negligible at best and detrimental at worst, okay, in the parameter regime. And that is because like we cannot really turn our coupling all the way to zero to effectively completely decorrelate the system. So we have some memory effects probably and stuff like that. This is due to the limitation in the control of D-wave. So that's probably where this comes from. But in the quantum case, which is the one that we are interested in, you can clearly see that the bigger the lattice size, the better I'm doing at resetting. So the cooperative effect is really present. And also that like higher magnetic fields, of course, like perform better in terms of average magnetization, which is kind of expected. Anyways, of course, higher local fields mean higher energy consumption as well, but that's another story. So transverse field, the takeaway of this is that transverse field is extremely effective at removing correlations, okay? So we really need the thing to have a transverse field component to be quantum to be able to exploit these cooperative effects, okay? So to take advantage of the lattice size. And what is the effect then on the fidelity? So here we concentrated on the quantum protocol, which is the one that works best, apparently. And here I'm plotting the same curves that I was plotting at the beginning. So fidelity of the reset operation versus the number of qubits. And you can see that you have the curves for individual resets so with no nearest neighbor, of the 2D Ising model, which has connectivity on average equal 4, and also we tried just turning on every possible interaction that we had at our disposal in the full connectivity graph of D-Wave, which is called the Pegasus topology, that has connectivity almost 15, okay? And on that model, we do not have any known phase transition, but we just did the experiment to say, well, screw, if more connection means more betterer, why not do it? And indeed, it seems that the more connection that you have, the more densely connected is your topology, the better you can exploit this cooperative effect, even if you do not have analytically a phase transition in your model. And temperature-wise, what do you have is that for the individual reset, we get, so if I do again the same fit of the temperature that I showed at the beginning, you have an effective temperature of the individual reset, which is in the order of 32 millikelvin, which is what we estimated independently by measuring the temperature at which the chip was sitting. While in the two cooperative protocol cases, we have a noticeable cooling effect with estimated temperature of 23 and 20 millikelvin, respectively. So this is really good, and you see that you kind of now you can reset a register of 300 qubits with very, very good fidelities with respect to what you could do otherwise by resetting them individually. So those are my results, and I want, if I have I think I have a couple of minutes. So if I have a couple of minutes, the QEI organizers ask the speaker to kind of give a spin of what does our talk mean to the quantum energy and put kind of in perspective. So that's my takeaway for the quantum energy initiative. So to me, this problem, this issue that we need a lot of, we need high fidelity states. So we want to prepare high fidelity, reset to high fidelity, do unitaries with high fidelity. I require for gate model quantum computer to have a speed up, to be useful in the standard sense of quantum computation, like Nielsen and Chuang textbook like. The problem is that assuming that your states are pure, or assuming that you are doing unitary dynamics or at high fidelity, effectively amounts to yourself asking your system to live in a space that has zero measure with respect to the total subspace of the total space of density matrices, right? So this subspace of pure states has zero measure with respect of the total phase space. And this burns a lot of resources in the process from a thermodynamical perspective, whether you use error correction, error mitigation, error suppression, cooling, whatever, to push up these fidelities towards the region where you feel comfortable doing your computation. So my spin on the lesson that this kind of process of achieving high fidelity by cooling or by collective protocol or whatever is that why don't we give a chance to something different by being more energy efficient, so burning less resources, dropping requirements on high fidelity, so using mixed states, and of course doing this we will drop high fidelity requirements and end up with something which is not provably the best algorithm, but maybe something that works well for some specific use cases. And to my mind, I have the talks of Gavin with the boson sampling for hashing, and Quack talk about the optical neural networks and stuff like that, which are not standard quantum computing algorithms that offer a provable speed up, but are algorithms that utilize low resources, do not have high fidelity requirements, and that probably can work very well on some very specific problems. So with that, I thank Michele, which collaborated and mentored me throughout this work and even much earlier, the access to the D-Wave computational time that was provided by Sineca, and the funding that pays my salary, and I thank you for your attention.
Hello, thank you very much. Very nice talk. I wanted to ask you about the beginning of your talk, basically, because you started with superconducting qubits. but the explanation was using a D-Wave machine. So I was wondering whether you are thinking of implementing this idea in actually a superconducting qubit device.
D-Wave qubits are superconducting qubits.
I'm thinking more, for example, if I want to run an experiment on IBM, right, which I believe is the data you had at the beginning, right?
Yeah.
Is there a way of applying this protocol, modifying this protocol to get something equivalent?
So that's a really nice question. So we were talking about it. Actually, is one of the things that we hope to do in the future. So I mean, on the type of qubits, the answer is D-Wave qubits are also superconductive. So it's basically the same technology. IBM has more control, higher fidelities. D-Wave is not really a universal quantum computer, as you know. But implementing these in a gate model device, let's put it like that, is definitely a thing that we want to try, and we are thinking about how to do it properly, because yeah, we need some low-level access or like to trotterize the Hamiltonian some way to implement this. So yeah, we have to think about it. The other issue of superconducting qubits, typically for this kind of protocols, is that they are usually scarcely connected, which might definitely impact the performance of these protocols. So probably it would be like also nice to put, like to confront this protocol working on a sparsely connected architecture like IBM or some other superconducting qubit gate model platform, and I don't know, trapped ions or something, which is typically more densely connected, or Rydberg atoms, stuff like that.
If you don't mind, I'll ask a second question on that plot as well. Is this what you get after applying a single reset gate, or did you apply multiple ones and got this dependence?
We also tried applying multiple ones, by which you get marginally better results, but yeah, implementing more helps a little bit. So you get like I don't know if I got the slides. Let me check. I had a couple of extra things. I don't remember. No, I don't have them. But yeah, it helps, but not like to avoid this dramatic effect of going down with the number of qubits.
Thank you.
Yeah. What? Where? Here? This one? No. That's the last one? Here. Okay. Oh, lattice one. Here meaning that each qubit is reset individually. So I'm not coupling them. It's just the baseline control. Okay. Yeah.
Did you look at your A of t being equal to B of t?
What? Sorry?
When A of t equals to B of t, your model has chaos.
Yeah, that's the critical point of the model. We actually never reached that point, so going back to the plot A of t, B of t. So that's the critical point. Okay, actually we go just below 0.5, we arrive at 0.6 if I remember correctly. Sorry, 0.4, because I'm looking in the other direction. So we start from 1, we go all the way down to 0.4 and we come back. So we actually never crossed the critical point, but we did do enough to turn on the transverse field, which is this A component here. Yep. You're welcome. Thank you.